So 1 minus q means p. So p raised to r into p raised to minus r, ultimately it becomes 1. So total probability is 1 here. Now when we take some properties, then this notation, in this notation small p and q, it is sometimes somewhat difficult to remember mean, variance, etc. So to correlate with binomial distribution, I just redefine this p and q. So let us take p is equal to 1 upon q and small q is equal to 1 upon p. Remember that small p is between 0 and 1. So naturally capital Q will be more than 1. So this is capital P and Q. So since P plus Q is equal to 1, because Q is 1 minus P, here we can say that 1 upon Q plus 1 upon P is equal to, Q is equal to P upon Q. And therefore 1 plus P becomes Q. Remember that Q will be equal to, capital Q will be equal to 1 upon P, and capital P will be Q, capital Q, so Q upon P, small q upon P. So when small p and q are given, we can find values of capital P and Q and vice versa also. Okay, so this is, now we express in terms of P and Q this probability function, then Px becomes minus RCx, this P raised to x, P raised to R, P means 1 upon Q, so it becomes Q raised to minus R, and minus Q, small q means P upon Q, minus P upon Q raised to x. So minus RCx, Q raised to minus R, minus P upon Q raised to x is the another form of negative binomial distribution, probability function of negative. So just now there are three very popular forms. One is this x plus r minus 1 cx p raised to r q raised to x. The other is this minus r cx p raised to r minus q raised to x. And in writing this in terms of capital P and Q, it becomes minus r cx q raised to minus r minus p upon q raised to x. So these are the three popular forms of probability function of negative binomial distribution. Now if you want to find the mean, suppose I just go for the properties. Mean means expected value of x. So sigma x px, sigma x running from 0 to infinity x into px means I may take minus r cx q raised to minus r minus p upon q raised to x. Of course I can use this form also, this or this also, but here if we simplify, I don't derive, but that mean will be rp. So generally for binomial distribution, and similarly negative binomial, mean was here n into p, here it becomes r into p. Remember that here it is small p, that is probability of success. Here capital P is not the probability of success, it is reciprocal of probability of success, remember. But to get this type of answer, I have redefined this small p and q in terms of capital P and Q. Similarly, we can find expected x square and then variance of x. So it becomes variance RPQ. If you remember, in that case it was NPQ. Then this is mu2, this is mu1 dash. Similarly, if you find third moment, it was NPQ into Q minus P. Here it is RPQ into Q plus P. Mu4, if you remember, it was NPQ into 1 plus 3 into n minus 2 PQ. Here it is RPQ into 1 plus 3 into R plus 2 into PQ. So this we can find this moments of various orders, and they exactly look like binomial distribution, the moments of binomial distribution, so that we can easily remember. So just to remember them very easily, I have redefined this small p and q. So similarly, we can define moment ending function mgf. And notation is say mxt is equal to expected value of e raised to tx. So sigma e raised to tx px. So it is p raised to r. So this way we can define sigma e raised to tx, then minus rcx q raised to minus r minus p upon q raised to x, and we can find this moment ending function. If we differentiate this with respect to t and put t is equal to 0, we can get first moment, similarly second moments and other. Similarly, we can find cumulative ending function, which is log of mxt, and from this coefficient of t raised to r upon r factorial of kxt will give you cumulants of different orders. One thing you just remember, in binomial distribution, last time we have discussed also beta 1 and beta 2. So in binomial distribution, beta 1 tends to 0, beta 2 tends to 0, beta 2 tends to 3 as n tends to infinity, and therefore binomial distribution approaches to Poisson normal distribution for large value of n. Here also, let us try to find out this type of property. Say here, if you find beta 1 means mu 3 square upon mu 2 cube. So mu 3 square means r square p square q square into q plus p square divided by mu 2 cube. So r p q cube. So it is 1 upon r into q plus p square upon pq. Similarly, beta 2 is equal to mu 4 upon mu 2 square is equal to mu 4 means rpq into 1 plus 3 r plus 2 pq divided by rpq square. So this is equal to 1 rpq gets cancelled, and divided this by rpq we get 3 rpq plus 1 plus 6 pq upon rpq. So this is beta 2, and here also if you observe, then beta 1 will tend to 0 as r tends to infinity. If we take limit as r tends to infinity, so since r is in the denominator, it is going to be 0. Similarly, this term will 0 because r is in the denominator, so it will tend to 3. So beta will tend to 3, beta 1 tends to 0, just like a normal distribution as r tends to infinity. So we can say that in a long run, or for large value of r, if number of trials is indefinitely large, then negative binomial distribution also approaches to normal distribution. This negative binomial approach is normal. So this is also similar property like binomial. Now, if you remember, in binomial distribution, I just give you some comparison of binomial and negative binomial. So in binomial distribution, if you remember, when n tends to infinity, means n is very, very large, p probability of success is very small, p tends to 0, and r into p is fixed, say lambda, fixed. Then binomial probability function of binomial distribution approaches to that e raised to minus lambda raised to x upon x factorial. Last time we have proved also, last Thursday, x running from 0, 1, 2 and so on. So which is the probability function of Poisson distribution. So in binomial distribution, Simon de Poisson has proved that when n is infinity, n is very large, p is very very small, and rp is a fixed quantity, then binomial distribution approaches to Poisson distribution whose probability function is this. Similarly here also, when r tends to infinity, capital P tends to 0 and r into p is equal to lambda, say fixed quantity, then the probability function px, which was x plus r minus 1 cx q raised to minus r and p upon q raised to x, okay, this was the probability function of negative binomial. Now this is equal to x plus r minus 1 r plus 1 r upon x factorial, q means 1 plus p q raised to minus r, p q means 1 plus p raised to x. If these are x terms and I take r common from each term, so r raised to x will be common totally. So it becomes, I write in reverse order, 1 plus 1 into, this is 1 plus 1 upon r up to 1 minus x minus 1 upon r upon this x factorial. Rp is equal to lambda, so it is 1 plus p means lambda upon r raised to minus r, and this is 1 plus 1 upon p raised to minus x. If I write p here, then 1 upon p plus 1 raised to minus x, and p means lambda by r, so this is r by lambda. So when we take limit as r tends to infinity here, then limit r tends to infinity, see this becomes 1 plus 0, 1 minus 0, 1 plus divided by x factorial, limit r tends to infinity, r raised to x, and this is 1 plus lambda upon r raised to r upon lambda raised to minus lambda, and this is, I take r raised to x here, so it is 1 upon r plus 1 upon lambda raised to minus x, and this is e raised to minus lambda, this is 0 as lambda tends to 0, this, and ultimately this becomes e raised to minus lambda raised to x upon x factorial. From this we get e raised to minus lambda, from this we get lambda raised to x, taking lambda common, and x factorial this one, and x turning from 0 onwards. So this way, from negative binomial distribution, under this condition we get Poisson distribution. Now, as Dr. Manish said earlier, when we take r is equal to 1, suppose here see it is x plus r minus 1 cx p raised to r q raised to x, this is the probability function of negative binomial distribution, where r number of successes, x number of failures, and x plus r means total number of trials, p probability of success, q probability of failure. Now if we take r is equal to 1, this was the probability of getting x failures preceding r success. When we take r is equal to 1, then xcx is 1, p raised to 1, q raised to x, so q raised to x into p, and this is the case of geometric distribution. So probability of number of failures preceding the first success, suppose a couple decide to have children until they get first male child, so that is the case of geometric distribution. So if the probability function is given by this formula p into q raised to x, where x starting from 0, 1, 2 and infinity and 0 otherwise, then we say that variable x, which denotes number of failures preceding the first success, is said to have geometric distribution, and here p is the parameter. Of course, p is the probability of success, again q is probability of failure. So from this negative binomial distribution, putting r is equal to 1, we get geometric distribution. So that way we can consider that geometric distribution is a particular case of negative binomial distribution. Now suppose, so here also in all the results of negative binomial distribution, just replacing r by 1, we get mean, variance, then moment generating function, cumulant generating function, etc. all can be obtained by putting r is equal to 1. Particularly when, see, suppose px probability function is q raised to x, p into q raised to x suppose, or q raised to x into p, x starting from 0, 1, 2 and so on, 0 other. This is a probability function of geometric distribution. Now suppose if I want to find mean here, expected x, so this is sigma x px, so sigma x, of course here is x starting from 0 to infinity, px means q raised to x into p, but here instead of 0 I may start 1 onward, then also there is no problem, because for x is equal to 0, this is going to be 0. So whether you start from 1 onwards or 0 onwards, ultimately value will be same. So I just write x, summation is over x, x starting from 0 to infinity or 1 to infinity. So this is p q sigma over x, x q raised to x minus 1. So here slightly the technique is different to find mean. We know that sigma q raised